Section 3.5 Factor Special Products. In this section we will factor a difference of squares and factor a perfect square trinomial. In section 2.6 we encountered two special products. The first was a difference of two squares. To factor the difference of two squares, it's often helpful to write each term as a perfect square and then apply the formula a squared minus b squared is equal to the factor a plus b multiplied by the factor a minus b. In Unit 2, when we multiplied conjugate binomials, we used FOIL, for example, to multiply 2x plus 3 multiplied by 2x minus 3. So first we would multiply 2x times 2x, which would give us 4x squared. 2x times negative 3, our outer, would give us negative 6x. Our inner, 3 times 2x, would give us positive 6x. And our last, 3 times negative 3, would give us negative 9. Now notice our like terms, our outer and our inner, add up to 0. So we're just left with 4x squared minus 9, which is a special product, which we call a difference of squares. So now in Unit 3, in this section, we're going to factor the 4x squared minus 9 back to the original two factors. So, and it's already been done here for us, but if you just draw your two sets of parentheses, if you recognize you have a difference of squares, you recognize 4x squared is the perfect square that you get from multiplying 2x multiplied by 2x. 9 is a perfect square that you get from multiplying 3 multiplied by 3. And the one sign will have to be positive and one will have to be negative, and you can always check your work by using FOIL. 2x times 2x is 4x squared. 3 times negative 3 is the negative 9. This was your F, this was your L. And then you can see your inner, 3 times 2x is 6x. And your outer, 2x times negative 3, negative 6x, adds up to 0. And that's why they went away, and they don't show up in your product. So when you factor differences of squares, a squared minus b squared, you can write your factorization as the factor a plus b multiplied by the factor a minus b, or because multiplication is commutative, you could also write it as a minus b multiplied by the factor a plus b. So let's factor some differences of squares. X squared minus 4. X multiplied by x is x squared. 2 multiplied by 2 is 4. We know 1 is going to be positive and 1 is going to be negative. If you want to check your inner and outer, 2 times x is 2x. Your inner and your outer, x times negative 2 is negative 2x. That's going to add up to 0. So you could write your answer as x plus 2 multiplied by x minus 2, or you can write it as x minus 2 multiplied by x plus 2. Nine x squared, a perfect square that comes from multiplying 3x multiplied by 3x. 16y squared comes from multiplying 4y multiplied by 4y. One will be positive, one will be negative. Or you can have the factors written in the other way because of the commutative property. Y to the 6th multiplied by y to the 6th is equal to y to the 12th. And 11 multiplied by 11 is 121. One positive, one negative. Five x multiplied by 5x is 25x squared. 1 multiplied by 1 is 1. 1 plus, 1 minus. X to the 3rd multiplied by x to the 3rd is x to the 6th. 3 multiplied by 3 is 9. one positive, one negative. Xy multiplied by xy is x squared, y squared. 2 multiplied by 2 is 4. One has a positive, one has a negative. Suppose a and b have no common factors. Then the sum of squares, a squared plus b squared, is not factorable over the real numbers. That is, a squared plus b squared is unfactorable or prime over the integers. So if you, we've just finished factoring something that looks like x squared minus 9, a difference of squares. And we've factored this. We know x times x is x squared. 3 multiplied by 3 is 9, and 1 is plus and 1 is negative. That's no problem. However, if you have x squared plus 9, now notice they say a and b have no common factors. In other words, there's not a greatest common factor that you can factor out. Okay? You still have to check to see if there's a greatest common factor. But other than that, if there's no greatest common factor that can be factored out, if you have a sum of squares, you may not factor it. A sum of squares cannot be factored. This is prime. It's unfactorable. Factor if possible. So notice we have t squared minus 36. We can factor this. It's a difference of squares. T multiplied by t is t squared. 6 multiplied by 6 is 6. One's positive and one's negative. T squared plus 36. Ask yourself if you could factor out a greatest common factor, which you can't. Since it's a sum of squares, this is prime, or unfactorable. All right. In section 2.6, we encountered two special products. We've just finished covering the first of the special products, the difference of squares. The second was a perfect square trinomial. Recall that the first and third terms of the trinomial are formed by squaring the two terms of the binomial, and the middle term was twice the product of the terms of the binomial. Understanding how the trinomial was created is key to recognizing and factoring perfect square trinomials. So let's just look at this example on the left. We have 3x plus 7 squared. So that means we're multiplying a binomial times itself, or we're squaring the binomial. So we could FOIL this. Notice we end up, when we do f, 3x times 3x. 3x times 3x is 9x squared. That's a perfect square. Then we do our outer. 3x times 7 is 21x. Our inner, 7 times 3x is 21x. Notice we're getting two of those. That's why down here at the bottom they have this 2. So the 3x is squared. We get two inners and outers. And then our last 7 times 7 produces, which is our last, produces our 49. So that's also a perfect square. So what we ended up with, this 9x squared plus 42x plus 49 is what we get when we multiply a binomial times itself, or when we square a binomial. We call it a perfect square trinomial. And just some things you can look at to try to recognize when you're dealing with a perfect square trinomial. Notice that the first term and the last term are perfect squares. 3x times 3x is 9x squared. 7 times 7 is 49. Also notice that this is positive. Notice this middle term is even. Okay? If you recognize that you're dealing with a perfect square trinomial, it makes it just a little more, it makes it more easy to factor. Okay, so The rest of this section will be factoring perfect square trinomials. So here's a procedure for checking for a perfect square trinomial. So look at the first and third terms and check to see that they're both perfect squares and that they have positive coefficients. And if they do, identify A and B and determine if the middle term equals 2AB or negative 2AB. And if the conditions above are met, we can use the patterns on the next slide to factor. So let's just look at these. We have 4b squared plus 28b plus 49. Notice it's positive, so that's good. Our signs will have to be the same. I notice this is a perfect square and this is a perfect square, so that's good. So let's just draw our two sets of parentheses. So this would be our F and this would be our L. So 2b multiplied by 2b would have to be 4b squared if it was a perfect square trinomial. And 7 multiplied by 7 would have to be 49. So let's just check our inner and outer. I'm not going to make this more difficult than it has to be dealing with those patterns. I don't want to confuse you. Let's just check to make sure our outer and our inner add up to 28b. 7 times 2b is 14b. 2b times 7 is 14b. Whoa. And notice that adds up to 28b. All right. And it has to be a positive 28b. So it looks like we're in good shape. So 2b plus 7 raised to the second. All right, let's look at the next one. Notice this is positive. Notice here we have a perfect square and here we have a perfect square. So I'm going to draw my two sets of parentheses. 3a multiplied by 3a is 9a squared. 7 multiplied by 7 is 49. And now let's check my inner and outer. 7 times 3a is 21a. 3a times 7 is 21a. But now my outer and inner this time need to add up to negative 42a. So remember, this means from an earlier section when we were factoring trinomials that your signs have to be the same. In this case, they both have to be negative. So instead of writing your answer as 3a minus 7 multiplied by 3a minus 7, we'll enter it as 3a minus 7 raised to the second. Okay. Perfect square, perfect square. This is positive. So 2y multiplied by 2y is 4y squared. Looking at my L, we have a variable in that term as well. 9z multiplied by 9z is 81z squared. I'll check my inner. 9z times 2y is 18yz. And 2y times 9z is another 18yz. If I add this up, I get 36yz. And I check up here, good, I need a negative 36yz. As long as these are both negative, I'm in good shape. So I will write my answer as 2y minus 9z raised to the second. D, 64y squared minus 48yz plus 9z squared. There's a perfect square. Perfect square. This is positive. See if it'll work out. If it's a perfect square trinomial, 8y multiplied by 8y will give me the 64y squared. 3z multiplied by 3z will give me 9z squared. 3z times 8y is 24yz. These are working out nicely. Sometimes they don't. 8y times 3z is another 24yz. This adds up to 48yz. And looking up here, you can see I need a negative 48yz, so these will be negative. So I'll write my answer as 8y minus 3z raised to the second. All right, 2 more to do. So there's my f. So 3ab multiplied by 3ab is equal to 9a squared b squared. My L, 1 multiplied by 1 is 1. Checking my inner, 1 times 3ab is 3ab. My outer, 3ab times 1 is 3ab. It needs to add up to negative 6ab, which it will as long as they're both negative. So this is equal to 3ab minus 1 raised to the second. And my final one for the day. I feel like I've been fighting with this computer a bit today. My f, 4x multiplied by 4x is 16x squared. 3y multiplied by 3y is 9y squared. If I check my inner, 3y times 4x is 12xy. 4x times 3y is another 12xy. I'm looking for it to add up to negative 24xy. And as long as these are negative, I'm good. So I will write my answer as 4x minus 3y raised to the second. All right, have a good day.